Chemistry, the Central Science, Chapter 5, Thermochemistry, Lesson 3. So in the last lesson, we talked about enthalpy, and now we're going to discuss two different ways we can calculate enthalpy of a reaction or a heat associated with a reaction. So the first one is constant pressure calorimetry. So this is the calorimetry that's basically open to the environment, which means that we're operating under atmospheric pressure. This is how most reactions occur. So we have our basic calorimeter, which is two styrofoam cups to provide some insulation. We have our thermometer to measure our temperature change. Water is in the calorimeter. And then we have our stir bar. So when we look at this, we're looking at what is the heat associated with our system that we have isolated here. So the Q of the system equals the Q of the water plus the Q of the reaction. Now, because these are the things that are contained within the calorimeter, we know that the Q of the system then has to equal 0 because whatever's happening to the water is the opposite of what's happening within the reaction. So therefore, we can say that the heat of the reaction is the negative heat of the water. This is simply our way of saying that the heat lost has to equal the heat gained within our system that we have defined here. So it's really easy then to measure what is the heat associated with the water. Well, we have a mass of water, the specific heat of water, and our temperature change associated with it. Once we find that, we can just flip the sign and then say, well, then this must have been the heat that was associated with our reaction or with a particular metal that we put in the solution, whatever it might be. So reaction at constant pressure is defined as enthalpy. So when we do constant pressure calorimetry, we are able to calculate the enthalpy for a given reaction. So whatever we calculate here for Q of reaction, that is our enthalpy. And if we know the mass of a solid that we're trying to dissolve in the water, we can determine our enthalpy in terms of kilojoules per mole, or we could also do it per gram. So in 50 milliliters of a 1 molar hydrochloric acid solution is mixed with 50 milliliters of a 1 molar sodium hydroxide solution, the temperature of the solution rises to 31.7 degrees. The original temperature of each solution is 25 degrees Celsius. What is the enthalpy in kilojoules per mole of the neutralization reaction? So we're going to assume the density and the specific heat of our solutions are the same as water, which is 1 gram per milliliter and 4.18 joules per gram Kelvin, respectively. So what's our net ionic equation? Well, in an acid-base neutralization, we know that the hydroxide ion reacts with the proton to form water. So sodium and chlorine are our spectator ions. So we need to figure out whether or not we have a limiting reagent. So in order to do that, we have to calculate a number of moles. We have our volume converted into liters. We multiply that by molarity to see that for the sodium hydroxide, we have 0.0500 moles. We do the same thing with our hydrochloric acid solution. It's the same volume and the same concentration, so we get the same number of moles. So that means that we are actually reacting these in our stoichiometric amounts, right? We would keep in mind that if one of these was bigger than the other, then we would use the smaller one in our final calculation as our limiting reagent. So we need to have a mass of water because we're using this equation here for water. We need mass, the specific heat, and the temperature change. Specific heat was given to us. We're mixing our two solutions together, so therefore our total volume is 100 milliliters. Because we assumed the density of our solution was 1 gram per milliliter, then we know that 100.0 milliliters is the same as 100.0 grams. To determine our temperature change, we look at our final temperature minus our initial temperature, and we see then that the temperature of the water rose by 6.7 degrees Celsius. We simply say that this is equal to the same amount of change in Kelvin because 1 degree Celsius change is the same as 1 Kelvin change. This is not saying that 6.7 degrees Celsius is the same as 6.7 Kelvin. However, the change is the same because both temperature scales change by the same amount. This is another way put as saying, if we converted this temperature into Kelvin, we'd add 273 here, we'd add 273 here, but since we're subtracting them, 273 minus 273 is 0. So our change in temperature is the same whether we're in degrees Celsius or Kelvin. So now we're going to multiply through in our specific heat equation, mass times specific heat times our temperature change. We all know that grams cancel and Kelvin cancels to be left with joules. So this comes out to 2800.6 joules. The question asks for it to be in kilojoules, and we pay attention to significant figures. So we have 2.80 kilojoules. We then remind ourselves that the Q of the solution, or the Q of water, equals the negative Q of our reaction, right? The heat gained is the heat lost. We see that the temperature increased for the water. That means that it must have absorbed some energy. It did. It absorbed this amount of energy. Well, where did that come from? It came from the reaction occurring when we did our neutralization. So we simply take our value and we flip the sign. So the Q of our reaction then is negative 2.80 kilojoules. Because we want to know what it is in kilojoules per mole, we take our kilojoules, we divide it by our number of moles, and we see that this comes out to negative 56.0 kilojoules per mole. So the other type of calorimetry that we can do is called constant volume calorimetry, which is also known as the bomb calorimeter. Why is this? Because we are combusting things in here. So we once again have water. We have our thermometer to measure our temperature change. We have our ignition wire to light our substance on fire. We have a stir. Our sample cup here is where you're going to burn your substance. We've got oxygen that can come in, right? Because if we're going to do combustion, we have to have oxygen present. And then this is sealed off, right? So this is the pressure within this system is going to increase significantly, right? But we're keeping the volume of it constant. In the constant pressure calorimetry, right, volume could have changed, which means we could have done a little bit of work, but it would be negligible unless you have PV work associated with it. And in the last example, we didn't have any gases, so there wasn't any PV work. So once again, we have Q of the system equals Q of the calorimeter plus Q of the reaction, because we're defining our system as what's contained within the calorimeter. So the Q of the system has to equal 0 because whatever heat is gained by the calorimeter is the same as the heat that is lost during the reaction. So we set these equal to each other and just say one of them has to be negative because heat lost equals heat gained. Now, because we're working within a calorimeter, we actually have a heat capacity for the calorimeter itself. So this is going to include the water and the actual calorimeter, whatever it is made of. So now we do heat capacity of the calorimeter times our temperature change, and that gives us the heat associated with our bomb or simply our calorimeter. We remind ourselves that when we do a reaction at constant volume, that we do not have enthalpy because enthalpy is defined as heat transferred under constant pressure. However, we can say that these are approximately equal to each other. There might be a time where you come across a constant volume calorimeter where it also includes the change in water. So it might tell you a temperature change in the water along with the specific heat of water and a heat capacity for the calorimeter. In an example like that, then it would simply be that the Q of the reaction is going to equal the sum of the excuse me, calorimeter and that of the water. So a 0.3175 gram sample of magnesium is burned in a bomb calorimeter that has a heat capacity of 3,024 joules per degree Celsius. The temperature of the calorimeter increases by 1.126 degrees Celsius. So we want to calculate the heat given off by the burning of the magnesium strip in kilojoules per gram and kilojoules per mole. So once again, we remind ourselves that the heat associated with the bomb calorimeter, or Q-cal is the same as Q-bomb, is the negative heat of our reaction. So we're using this equation here saying that Q equals the heat capacity of the calorimeter times the temperature change. The heat capacity was given to us, And the temperature change was given to us. It just says the temperature increases by this amount. It didn't matter where it started or where it finished because this was our change. Temperature is a state function. So we plug things into our equation, multiplying our heat capacity times our temperature change. We see that that comes out to 3,405 joules. So that is the heat that was absorbed by our bomb calorimeter. That then is equal to the heat that was lost by the reaction. So this was the heat then that was given off when we burned our magnesium strip. Same amount, opposite sign, just to show that this is the heat that was lost. So it wants to know what was the heat in kilojoules per gram. So once again, we have converted our joules into kilojoules. We take the grams of our original sample. So negative 3.405 kilojoules divided by 0.3175 grams gives us negative 10.72 kilojoules per gram. It also asks us for kilojoules per mole. So we're going to take our mass, we divide by molar mass to find our moles of magnesium. Right? We look at our periodic table to find the molar mass of magnesium. So we get 0.01306 moles. Kilojoules divided by moles gives us kilojoules per mole. So negative 3.405 kilojoules divided by 0.01306 moles equals negative 260.7 kilojoules per mole. So this tells us what the heat is associated with burning magnesium on a molar basis. The last part of this lesson deals with Hess's law. And Hess's law is based off of the fact that enthalpy is a state function, which means that we can look at an enthalpy for a reaction as taking part in one step or a series of steps, but you're still going to have the same value. So the overall reaction that we're trying to get to is the enthalpy of formation of carbon dioxide. So we take carbon graphite, which is its most stable form, plus elemental oxygen to get to carbon dioxide. So over here, this shows us we start with our reactants. If we do this in one step, we get to our carbon dioxide. It gives off 393.5 kilojoules of heat. If instead we take this in two steps, we take our graphite plus our oxygen, and we form carbon monoxide and a half a molecule of oxygen, we see that that process is exothermic as well, and that value is negative 110.5 kilojoules. Then we take our carbon monoxide, react it with a half of mole of oxygen to get to carbon dioxide. So we see that that is exothermic with a value of negative 283.0 kilojoules. If we add negative 110.5 plus negative 283.0, we see that that value equals our negative 393.5 kilojoules. So once again, if we just think of this as just like walking upstairs or walking downstairs, it doesn't matter if you take two stairs at a time or you take one step at a time, you get to the same place. And that's the way Hess's law works, because it is a state function. This is why we can do this. So practicing with Hess's law. From the given equations, calculate the standard enthalpy change for the reaction of aluminum with iron 3 oxide to form iron and aluminum oxide. So this is our desired equation, and now we play a matching game because we need to make sure that we get everything down here to match what's up here, meaning that we need the same amounts, and we need to make sure that reactants are reactants and products are products. So I always just start with the first thing I come to. I see that I have two aluminums. I look at this first equation and see I have two aluminums. I also notice that the aluminum oxide is a product and aluminum oxide is a product over here. So I don't do anything to this equation. I leave it as it stands. I come to my Fe2O3. I see that it's a reactant. In this equation, it's a product. So that tells me that I have to flip this reaction, which then is the same thing as saying I multiply this by -1. In flipping this reaction, I've turned my iron 3 oxide into a reactant, and I've put my iron as a solid as a product. So everything is matching now. You can only manipulate an equation one time. So once I've flipped this reaction, I write that down here to show that things are going to cancel out and I get back to my desired equation. This is your check for your work to make sure, that everything was done correctly. So indeed, I see that my 3/2 of oxygen cancels out. So because I have my desired equation, then all I need to do is add my two enthalpies together. And I see that negative 1601 kilojoules per mole plus 821 kilojoules per mole gives me negative 780 kilojoules per mole. So then this is the enthalpy of reaction for this equation. And if we want to remind ourselves, this is an oxidation reduction. It's a single replacement. Aluminum replaced iron, kicked it out, and we get aluminum oxide. So aluminum was oxidized, iron was reduced. So one more practice problem here. So we want to figure out how can we calculate a standard enthalpy change for when we react 2 carbon as graphite plus 3 molecular hydrogens, right, elemental form of hydrogen, to form ethane as a gas. So here's our given equations. These are the equations that we're going to manipulate to get so that we have this is a reactant, this is a reactant, this is a product. We have 2 of these, we have 3 of these, we have 1 of these. So once again, I look for my first thing. All right, this shows up in the first equation. There are 2 of them. There are only 1 down here. It's a reactant here. It's a reactant here. So I don't have to flip the equation. All I have to do is multiply through by 2. So I've done that down here. I've done my distribution, my distributive property, and I multiply the energy as well. I have 3 moles of hydrogen. Here's my equation where I have hydrogen. I only have 1 of them. It's a reactant. It's a reactant. I do not have to flip the equation then, but I multiply this through by 3, which means I multiply the enthalpy by 3. So 3 hydrogens plus 3/2 oxygen yields 3 waters. So once again, it's a distributive property, right? This is like a system of equations. Last but not least, we have our ethane as a product, and we have 1 mole of it. Here I have ethane as a reactant, and I have 2 moles. So I have to divide everything through by 2, and then I also have to flip the equation. So that's the same thing as saying I'm multiplying by a negative 1/2. So I flip the equation, so my products become my reactants. I divide everything through by 2, so I have 2 moles of carbon dioxide, 3 moles of water, gives me 1 mole of ethane, and 7/2 moles of oxygen. Then I go through to check to make sure that I did indeed get to my balanced equation. My graphite, my hydrogen, and my ethane should remain because that's the equation I'm trying to get to. So then I look here and I see I have 2 moles of oxygen. I have 3/2 moles of oxygen. So that's the same thing as saying 3.5 moles of oxygen. 7/2 is the same as 3.5 moles of oxygen. So all of my oxygens cancel out. 2 moles of CO2, 2 moles of CO2 cancel, 3 moles of water, 3 moles of water. So this here tells me that yes, I did the equation manipulation correctly. So that means that the things that I did over here to the enthalpy will be correct as well. So I do my calculations. I've multiplied negative 393.5 times 2 from up here, negative 285.8 times 3 from up here, and negative 3,119.6 times a negative 1/2 from up here. So I do the math individually, I add everything up, and I see that this reaction then equals negative 84.6 kilojoules per mole. So to react graphite with molecular hydrogen to form ethane gas, it is exothermic, and the enthalpy of reaction is negative 84.6 kilojoules per mole.